a very important topic that comes as curse of dimensionality. Okay, what is this dimensionality and how it is affecting to your data mining task? Now we saw the table with the different attributes such as name, okay, his tax and his salary and all the other details. Okay, if it was only for 3 or 4 such attributes, it does not impact that much on the data mining task. Okay, but if it is keep on increasing, so suppose there are some experiment conducted on a chemical, okay, and they are recorded for the different attributes on the various observation. Okay, in that case it will create a huge data along the column ones. Okay, there are attributes and the records and so on. Okay, in that case it will create an impact on the kind of data mining task you are doing. Okay, if it happen to be classification, it will impact on the classification task. If it is clustering, then it will impact on clustering. So what you need to do in that case, you need to select the best attribute that are available in the given table and use it for that. So that is the curse of dimensionality, and there is a solution also exists for the dimensionality. So these are the technique which are applied in order to reduce the dimension. Okay, so what are those? Principal component analysis, singular value decomposition, and other supervised or unsupervised technique which are used for the purpose of reducing the data dimensions. Okay, now what you are actually achieving, you are achieving the reduction of, say suppose it is not very important data for data mining purpose, you are reducing that out. Okay, now we will take out some of these technique. Okay, understand how these techniques are working. Okay, not in depth, but at least the principle of this working we will identify. Now let us take first one. It is called as principle. I will just discuss the idea behind this principal component analysis. Okay, we are not going through the in-depth of mathematics. So suppose you would like to do it, you can further study what the mathematics of this principal component analysis. Let us consider a two-dimensional data plane. Okay, so in the plane, these are the axis, y-axis and x-axis along here. Okay, suppose I take any point on this particular plane, two-dimensional plane, say suppose this point. How many attributes are required in this case? How many? Say suppose x1, y1. Any data on this two-dimensional will have 2. So I can say this is two-dimensional data. Okay. Now let me take single line. Okay. Let us take a origin here. From this origin, I just simply measure the length of one particular line. Say suppose I come here, okay, say this is my x1 or this is my x2. Okay, these are just measuring these lengths. Okay, length 1, okay, length 2 and so on. So how many dimension here it is required? 1. Okay, so this is 1 dimension. Okay, suppose if I map this particular data from 2 dimension to single dimension. Okay, suppose if I map it here on any of these lines. Okay, say suppose line is present here and I map it on this one. So what exactly it is doing, the data point which is available here on 2D plane is actually mapped to the line over here. Okay, now what you are effectively done is you reduce 2 dimension to single dimension. So what kind of line you have to select? You have so many lines to select. Okay, you can have a infinity number of lines are possible there. So you can choose something like here or here, somewhere here. So there are multiple lines on which you can perform this projection. Okay, and each time you will get a different representative. But what will be the best line? Okay, that you have to decide. Okay, if I have a whole distribution of data, okay, if it is distributed something like this, okay, basically you would like to find out the how it is distributed, and if it is line is going through the maximum spread, okay, something like this, you would like to select the line which is going through that all the points and covering the maximum spread. Okay, so if you are able to find out this one, then you go for performing the projection. Okay, once the projection is formed, the data which was there on two-dimensional, now it is converted to single dimension. Okay, now how do I decide this particular direction or the line? It can be done with the help of eigen values and eigenvector. So I take covariance matrix of this particular data, and then I can build upon that one. Eigenvalues and eigenvector can be determined. The maximum, the eigenvector with the maximum eigenvalue is one that is selected here, and then you can also select multiple depending on how much dimensionality reduction you want to achieve. Okay, so this is the fundamentals of principal component analysis. Okay, you can further read upon that, okay, and understand how the this one is working. Okay, how the eigenvalues are computed, how the covariance matrix is constructed, and so on. Okay, we will not go in depth of that. Okay, now there are feature subset selection technique. Okay, so what I want to do is, if I have a huge amount of data and also different attributes, I want to select some of the attributes which are most important for my task. Okay, I don't want to take whole thing, so that task itself is called as feature subset selection. Okay, redundant feature you want to remove, irrelevant feature also you would like to eliminate, so that's the task of feature subset selection. So what are the different types of techniques are available for feature subset selection? Go for a brute force technology. Okay, just select whatever you wish. Okay, in that case the result is also same, whatever it wishes it will impact, but go for a better one. Okay, you have a technology and then go for a embedded approach. Okay, in the embedded approach, these are the algorithm, okay, which are embedded with the estimation of feature value, impact of feature value, okay, or the importance of the feature value. For example, Gini index is used in the decision tree classification technique. Okay, there it is completely embedded along with the algorithm. Okay, we'll come back to that one. How do we estimate everything? Okay, we'll perform the calculation. Those are called as embedded approaches. Okay, and filter approaches are the one separate task before the taking place of data mining task. Okay, before that one, the filters are applied, and then the feature which are irrelevant are removed from the data. And the wrapper approach, the use of data has a black box along with the data mining algorithm. These tasks also used, but there is a difference between the filter and the wrapper approach, is that the wrapper approach is a part of the algorithm itself. Okay, in the filter it is separated out. This task is maybe totally different from the data mining algorithm what you have written. Okay, so that's the difference. So a totally different process. Embedded is a totally inside that part of that, wrapped with the algorithm. So three different techniques are available for feature subset selection. Now in the case of feature creation, you would like to estimate the different features. Okay, you would like to create and observe. Say for example, you would like to look at the face recognition, then you would like to create the measurements which are required for the purpose of face recognition. Say something like, what is the width of the eyebrow, what is the length of the face, okay, what is the length of the nose. Okay, these will create your features. Okay, and the phenomenon or the process itself is called as feature creation. Okay, now there are different domains, so there are different feature creation technologies. Say mapping of data to the new space, feature construction, feature domain specific. So these are very domain specific tasks, and they need to be also perform some kind of transformation. For example, you would like to work from the frequency domain, for say in the frequency domain rather than working on the time domain, then you will perform the Fourier transformation. Okay, there is advantage of going from time domain to the frequency domain. So in such case, we have different type of transformation. Okay, in data also we would like to expand the data, look into the minor detail of the data. You can use the log of the function. Okay, so you can do many of these things. Similarity function or dissimilarity function are required when I would like to observe two objects which are how much they are close or how much they are far away. Okay, suppose I am creating the clusters. Okay, then I would like to observe how they are close to each other. If they are close to each other, I would like to keep these objects in a single cluster or a single group. Okay, if they are very far away, then I would like to create different cluster for that. Then there is a requirement for me to observe the similarity or dissimilarity among two different objects. Okay, there are different methods available for performing the similarity or dissimilarity tasks. Okay, depending on the what data type you have, there are different techniques which are available. Say for example, Euclidean is a one good example for finding the distance between two objects. So it also finds the how much closer the objects are. So nominal, ordinal, you have different techniques for finding the similarity or dissimilarity measurements. Euclidean is a good example. It can take different attribute, compute the distance between using the square root of a given square of individual differences. Okay, so we will take a look into this one more closer when we are actually doing the clustering algorithms, but in this case just for covering this syllabus here, so you have x and y different attributes. These are the attribute in two dimension, and then I would like to compute the distance between the two, and then you can compute using the Euclidean distance. Okay, so it will create the proximity matrix, whatever the matrix that is created between x1, x2, x1 against those, it will create a proximity matrix. Minkowski is a general form, okay, of the Euclidean distance. Okay, rather than having a square root as a 2, okay, root of 2, then the generalized version is called as Minkowski. Okay, the R is used in this factor, okay, to decide the parameter. With the changing R, we will get different equation. So suppose if it is R equals to 1, okay, you will get CT block Manhattan distance measure. Okay, if it is R equals to 2, you will get Euclidean distance. Okay, if R is infinity, there is no such thing as infinity, but I will tell you how to compute this. This is called as supremum. Okay, supremum distance. Okay, so how do we let us take an example of applying Minkowski on different R values. Okay, now this is the table that is given. Okay, you can also observe the points x5. Only two-dimensional data point is collected, and I will take R equals to 1. That is basically absolute difference between the 2 points. Okay, now let's say x, say p1, p2. Okay, if I take that difference, then how do you apply? So this is the equation. Okay, you have to apply with taking. Okay, so this is my equation, and R you have to set it to 1. Okay, so R equals to 1. What will happen when R equals to 1 in this case? Distance it will become. So this is sum of, okay, P, say P, there are two values, Q1, okay, plus P2, Q2. So this equation I can apply on the given table here, okay, and then I can compute the distance between, this is Manhattan distance, distance between 2 points P1, P and P1 and P2. Okay, so you have to substitute those two values and then compute the difference. Okay, so here it will be P1 and P2. Okay, so you can substitute 0 minus what is P2 plus, okay, 2 minus, this case is it 4? Yes, P1, P2 is 4. Okay, so in the same manner you can compute for the others. Okay, Euclidean distance you need to take square and then take the square root. Okay, but in the case of supremum, okay, you perform the same task, but you will choose the maximum out of these two. Okay, this is done with the Manhattan distance. Suppose I am interested in computing the supremum values, so you have to take the maximum. So if I am interested, then you have to take the maximum of difference between the two elements, say P1 minus P1 here. So if there are two attributes only, and then P2. So whichever is the maximum, you have to select that as a difference. So that's what you will do it in terms of supremum. So these are the different ways of finding the similarity or dissimilarity values. Okay, and these should be the properties of these distances. Okay, they should measure the distance from the origin. Okay, and it should be greater than or 0. Negativity is not allowed in this distance. And if you compute the distance between P to Q and Q to P, both should be same. That's the logic to have it. And if there are 3 points in between, there is 1 point, the 2 points calculation should be greater than directly going to that point. Okay, so that these are some of the properties of similarity, and yes, there are some specific for the binary vector. Okay, binary vector does not have real values like greater than 1. Okay, so it has the values between 0 or 1. In that case, you need a different ways of computing the similarity or dissimilarity matrix. One is simple matching, another one is also called as Jaccard coefficient. Okay, so we will see how the simple matching is done. Let us assume that these are the patterns. Okay, these are the patterns. 1 0 0 and another one is 0 0, something like this, and I would like to apply simple matching coefficient on the two matters. Okay, then initially it is observed that how one or two elements are matching. Okay, now suppose if I take the first position. Okay, first position it was 0 and in the second pattern it was 1. How many such things are happening? Okay, in the first time it should be, let's take example here, is easier. So you observe first one M01. So how many times there was 0 in the object 1? Okay, suppose 0 1 1 0 0 and then there is object 2. Okay, and this is 0. Okay, and this is say 1 and this is 0 and this is 1 0. Okay, now I would like to compute how many times it was 0 and there was also 0. How many times? 1 time, 2 times. 1 0. How many times it was 1? 1. And no time. Yeah, 1. And it was 0 and this is 1. How many times? Okay, and use these m values in the equation. Okay. So in the same manner, Jaccard coefficient also uses the m values. Okay, frequency values to compute the coefficient. Cosine are more general form. Okay, you can use it for the vector consisting of numerical value. The cosine is using the dot product of the vector and the magnitude of that divided by the magnitude of vector. Okay, so I hope it is very easy. Just take dot product and then divide by magnitude. Okay, so this is another extended Jaccard coefficient. Now Jaccard coefficient was applicable for the binary values. Now this extended version is applicable for the real values also. So it is a dot product then divided by magnitude minus dot product. Okay. In this presentation we discussed about cause of dimensionality, dimensionality reduction, and similarity and dissimilarity measurements. Thank you for listening to this presentation. Thank you.